Welcome back, everybody. Let us start with the D and F block in this summary series. I will keep this session short because there is nothing much to talk in F block elements. These are the elements which are of very less known reactions to us. So we are saved. We have to know, we have to understand, we have to learn very less number of reactions compared to S block and P block reactions. But of course, D block has got very beautiful molecules. For example, K2Cr27, potassium dichromate, permanganate, to name a few molecules. And these are the molecules which have got immense usage in organic chemistry because they are very strong oxidizing agents. So let us dive into our D and F block elements. I am your teacher, Dr. Lakshya Kathuria, and I welcome all of you to this beautiful platform of PW. Let us start, everybody, and see what we are going to actually start with. We will be discussing entire D block elements, their properties, their physical chemical properties, some special cases also. Very often people call them exceptions. I don't like this word personally, exceptions. If we have an explanation to something, that becomes a fact. That is not an explanation. If you cannot explain anything, that becomes an explanation. That becomes an exception. But in my views, there is nothing called an exception. Those things are still under study. So we cannot claim that. We can't say that we do not know, or rather we can't say anything about it because we don't know much about those things, right, everybody? Let us start talking about D block elements. And out of so many of the compounds of D block, we will particularly discuss chromium compounds and manganese compounds, and finally lanthanide and actinide. This is of very high weightage in your board examination also, plus your NEET and JEE examination also. At least 1 to 2 questions are definitely expected to come. Okay, so let us pay 100% attention. These are the elements which are included in D block. So starting from this 3D series, this is called 3D series, everybody. This is called 4D series, that's 5D series, and the last one is 6D series. I have picked this periodic table from the very recent periodic table released by IUPAC, IUPAC. Okay, so why is it called 3D series? Why is it called 4D, 5D and 6D series? Because the last electron is actually entering in the 3D orbital. And here the last element, in all these molecules, the last electron enters in 4D. And the next one, 5D, successively in 6D. Correct, everybody? That's the meaning of 3D, 4D, 5D and 6D series. So if anybody talk to you, if anybody discuss with you, name any 3D element, those are the elements which receive the very last electron in their 3D orbital, or then 4D, 5D, 6D orbital. So these are the elements ranging from 57 to 71 atomic number. They all are kept in the category of lanthanide. This is also we are going to discuss, and ranging from 81 to 103, all those elements are included in actinides. Okay, the very first element here would be lanthanum, and here actinum. So let's begin, everybody, and discuss how we have to categorize, or what are the properties of D block elements. So as you've seen in the previous slide, everybody, these are the total number of groups starting from 3 and up to 12. So total number of groups are 10. Why 10? How do we know? Because D subshell can accommodate max 10 number of electrons, max 10. So this has got 1, 2, 3, likewise up to 10 electrons are present in the last block of D. Okay, let's see how do we actually categorize transition elements or D block elements. All these elements which I had showed you are D block elements, but not all of them are known as a transition element. That becomes the very first question for today's discussion. According to IUPAC, that the transition elements are defined as the metals which have got incomplete D shell, incomplete D subshell, if they are in their neutral state or considered their highest stable, most stable oxidation state. So zinc, for example, zinc, mercury, cadmium, these are the elements which have got 3D10, 4D10 and 5D10 type of electronic configuration. So according to IUPAC, when I consider them in their neutral state, they are not incompletely filled. They are 100% completely filled. Correct, everybody? Also, if I consider zinc most stable oxidation state compound, that's zinc 2 plus. The other electrons present along with 3D is 4s2. Here also 5s2 and here 6s2. And when it comes to remove electron, we have to remove the electron from the outermost orbital, as everybody know. So these two electrons will be removed, but the d electrons are untouched. So even when zinc is 2 plus, the d orbital is still completely filled. Likewise, in the case of cadmium and mercury, there is out of these three, none of these elements are having any incompletely filled d shell. Therefore, they are not considered as transition elements. They are not considered as transition metal atoms. Rest, all of these are considered as transition metal atoms. So this is the definition. So this becomes one of your question: why zinc, cadmium, mercury are not transition element, though they are d block elements. Okay, everybody. This is the general configuration of these elements, that n minus 1. This is known as, this is the valence shell. This is n is the valence shell, the last one. And just before that, there is a n minus 1d. Energy wise, n minus d is going to be of higher energy and ns will be of little lower energy. So following Aufbau rule, we will be filling up ns first. Once it is filled, then we start filling electron in n minus 1 d orbital. Correct? Okay. So this is 3D series, which has got 10 elements starting from scandium up to zinc. Then we have 4D series starting from ytterbium up to up to cadmium. Correct, everybody? These are the elements present over here. Okay, then we have 5D and 6D series. We will be listening to them. We will be studying them separately. We don't study them in lanthanum and actinum. They are not studied together with 3D and 5D series because they have got different properties. Lanthanum and actinum, they are separately studied. These are 5D series. Apart from lanthanum and actinum, every other series elements you can study together in the format of D block discussion. Okay. So there are some elements which have got notable electronic configuration. I have picked all of those which are important for your board examination perspective, also for your JEE mains, as well as for your NEET examination. So what is special in their electronic properties, everybody? Let's pay attention. Chromium as a first example, its normal configuration should have been 3d4 for 3d4 5s2, because as I said, Aufbau principle says until s orbital or lower orbital is completely filled, lower energy orbital is completely filled, you cannot start filling up the electron here. Correct? So 4s is supposed to be filled completely, then the electrons are present in the d orbital. This is the normal electronic configuration of chromium. But this electron sacrifices itself, rather unpair itself. That's the correct terminology. Unpairs itself and produces such kind of electronic configuration where we have 5 unpaired electrons present in 3D and 1 unpaired electron present in 4s. So total number of unpaired electrons present in chromium is total number of electrons are 6. Correct? How many? 6. I'm sure you must have watched all the what was those movies known as Marvel movies, right? So I'm sure you must have seen Black Panther. You must have seen there is a what was that? The one with the hammer? Thor, huh? Thor, yeah. So let's take an example of Black Panther. Black Panther has been shown, or if you consider, if you recall that movie, there was a hypothetical metal shown, vibranium. Okay, so in reality, in this real world, I have to recreate, or if I have to mimic, or I have to name any element known to us so far, which is similar to vibranium, is chromium. Okay, is chromium, because of its very hard nature. Chromium is very hard. Okay, so chromium can be a substitute or can be one of the alternative of vibranium in real world. Okay, But that's not the agenda for today. I am here to tell you the exceptional or different or abnormal, rather, abnormal electronic configuration. Chromium has got 3d5 4s1. Likewise, copper has also got 3d10 4s1. It was supposed to be 3d9 4s2, but it is not so. Why? Again, this number, one of the electron from 4s, unpairs itself and gets into 3d, excites itself into 3d. Why is it happening? Because half-filled electronic configuration is very stable. Fully filled electronic configuration is also very stable, rather extra stable. These are extra stable. Why are they extra stable? That also you should know. This becomes your second question for today. Why are they extra stable? I will give you the answer to this question near the end of the session. I want you to comment or write in the comment box. What do you understand? What is your analogy behind it? What is your perception behind it? Why chromium and copper let their electron from 4s to jump? Why is this unpairing happening? Why is this how is this possible? Okay. Okay. Then in the 4D series, we have got few elements, but more than 3D series. I don't want you to remember all of these, but specifically you should remember molybdenum. That has got 4D5 5s1. Let me go back to the periodic table and I will show you just below chromium there is molybdenum. So whatever behavior chromium shows, the same behavior molybdenum also shows in terms of electronic configuration. But interestingly, tungsten doesn't do that. Tungsten has got normal electronic configuration. It doesn't do that abnormal electronic configuration. Okay. Hence, I did not include that here. Did you notice I have no tungsten over here? Clear, everybody? Okay. Now, when we go to the next one, which has got a 4D series, palladium, I want you to put here star, moon, Mars, Earth, whatever you wish. Please notice this is the only element which has got no electron in S. This has got no electron in S at all. All the electrons are now present in 4D. And due to this reason, palladium has got a huge catalytic property. You must have studied palladium used in organic chemistry at various places, specifically in reduction chemistry, heterogeneous catalysis. So do remember, guys, please remember palladium has got nothing in S. 5s 0. Then I want you to pay attention to platinum also. Platinum has got 5d96s1. And this much is enough, guys. So let me mark palladium, you should remember. Platinum also you should remember. Silver also to some extent, if possible for you to remember. Then coming here, molybdenum you should remember. Copper also you should remember, and chromium. These are the two most important from your board perspective. Okay, guys, moving ahead. So we have to discuss what about their physical properties. Melting point and boiling point comes at the first while we discuss physical property of any element. So the transition elements, we know these are not the transition elements. Zinc, cadmium and mercury, they are not transition element. So except these, every other element in the D block is hard in nature. They are of hardness. So they will have some high melting and boiling point as well. But they relatively have very less melting and boiling point. And what is the reason behind melting point, boiling point, high melting point, high boiling melting point, boiling point? Is that if you have high number of unpaired electrons, there will be strong metal-metal bonding. There will be strong metal-metal bonding, and then you need extra energy. You need high amount of energy to separate them. And once they are separated, then only you can boil. Then only you can boil the metal. So the melting point and boiling point are high due to the involvement of greater number of electrons in n-1d orbital in addition to ns electrons in the interatomic metallic bonding. That's what I said. If the number of electrons are unpaired more, there are high chances for metal-metal interaction, metal-metal bonding. I am saying interatomic metal bonding. Okay. So now we can see that in the form of a graph. You can say that, sir, it looks like chromium will have 6 unpaired electrons, correct? 3d5 4s1. Likewise, molybdenum will also have, right? Tungsten also has but 5. So these are the one. So do you see the peak here in this 3D series? How to read this graph? Let us first come out here, everybody. Melting point is on the y-axis. Atomic number is on the x-axis. As the atomic number is increasing, there is no guarantee that there is no straight away flow of increment in melting point or boiling point. And why should that be happening, by the way? Why should it be happening? Because as you are moving further, the number of electrons are increasing and it will start pairing up. The electrons will start pairing up. So these are the elements: molybdenum, chromium, tungsten. They, in their particular series, they have got highest melting and boiling point. Now you might be saying, sir, manganese also has got 5 unpaired electron, but exceptionally this has got very relatively less melting point. Relatively less melting point. Do you see that titanium, vanadium, they are having higher melting point than manganese itself? So this you should remember. You may be asked in this, you may be asked in the question to arrange them in ABCD, to arrange them in terms of their melting and boiling point. So you should know that manganese has got lesser melting point than titanium itself. So titanium is harder than manganese. Harder in the sense having higher melting point and boiling point. Okay, moving ahead, everybody. So this becomes the reason. Frequent metal-metal bonding in the compounds of their heavy transition element. They are the one which have got relatively higher melting and boiling point in their respective series. In 3D series, chromium. In 4D series, molybdenum. 5D series, tungsten. Okay, good job. Moving ahead, everybody. Now, enthalpy of atomization is something similar to how the electrons, how the atoms, they want to separate. They want to get separated. So you will need higher amount of energy if the metals like to be with each other. You need less amount of energy if metals, they don't like to be with each other. We have to figure out, we have to study that. So here in chromium, you have got 3d5 4s1 type of electronic configuration. There are total 6 number of unpaired electrons. How many, guys? 6 unpaired electrons. Now molybdenum has got how many unpaired electrons? It has got 5 here and 1 more here, correct? So in this situation, what is going to happen? As the number of unpaired electrons are going to increase, as the number of unpaired electrons go up, so that interaction, metal-metal bonding also start becoming stronger. They also start becoming stronger and stronger and stronger. So they have maximum number of unpaired electrons. They will have maximum number of unpaired electrons. This is for just the comparison purpose, guys. So tungsten, it is shown to have 4D. This should have been 5D, by the way. This should have been 5D5 and this is 6s1. Just for the comparison purpose, I have made one of the electron unpaired once again. But in reality, it is not so. In reality, tungsten does not let its electron go here in the 6s. It does not let this electron get unpaired. So there will be such kind of electronic configuration which is not similar to chromium and molybdenum. Chromium and molybdenum, they will let this electron pair get unpair. This electron get unpair. Here also it happens, but in tungsten, the chances are very, very, very thin. Very thin. Okay. As the number of unpaired electrons will increase, metallic bonding will also increase. You will need more amount of energy, more amount of enthalpy to break down, to separate those metal atoms. So enthalpy of atomization will also increase. So in this graph, it is now evident. In this graph now, it is evident. Higher amount of energy would be required in this entire series for chromium. Correct? This is the highest. For here, molybdenum also highest. Correct? Okay. Good. Now, moving to the atomic radius, we know that when we move from left to right, the size is supposed to decrease. And that's actually happening. But is it a straightforward trend? No, from here up to this point, it seems to be decreasing. Then it seems to be becoming some sort of constant trend, some sort of constant. Here also almost constant. So I want you to remember that in Ficoni, FeCO and Ni, you may include manganese also. You may include, the difference in the sizes are not very great. So manganese, iron, cobalt and nickel, they have similar atomic radii. Let us see why is this happening. We were expecting the size to decrease as we move from left to right. The less number of electrons, read this point, guys, the less number of electrons in the d orbital, what is going to happen from here to here up to you reach manganese, the number of electrons are present d5, and when you go past manganese, number of electrons will become d6, d7 and then d10. Number of electrons are increasing. As the number of electrons increase, electron repulsion starts becoming dominant, due to which the size starts becoming bigger than you expected. You were expecting it to decrease, it to shrink, but number of d electrons are increasing, and d electrons, they don't like each other remaining at the same place, they start repelling each other more. Therefore size starts increasing little bit. Does it increase too much? Does it go beyond the size of the starting material, starting element, titanium or the other one? No, it doesn't happen that way. This increases to some extent. You were expecting it to go a little down. See this, guys? You were expecting this graph to go a little down. You were expecting this also to go a little down. You were expecting this also to go a little down. But is it happening? No, this is not happening that way. Past manganese, the size starts increasing a little bit. But if someone asks you which element they have got similar sizes, you can include FeCO and Ni, or sometime you will see that the data says manganese also is included. Sometime in the questions they say manganese also. So this becomes the third question for today. Why is the size of manganese, iron, cobalt and nickel, they are similar? I'm not saying same, they are similar. So reason is this has got number of electrons. If you were expecting the size to go smaller, but d electrons, increment in the d electrons, the size is supposed to increase. So there will be a constant competition, healthy competition between these two factors, and overall there will be overall there will be no effect. So size remains almost the same. Okay, I hope I am clear with this point. So now you can see that when we move from top to bottom, the size is supposed to increase. This white line represent the 3D series element, and then 4D series yellow line, and then the next one represent 5D series. As the number of electrons are increasing from top to bottom, the number of electrons require more space to accommodate themselves. So size should definitely increase. Of course, it should increase. But the size of 3D to 4D, when you move from, let's say, titanium to zirconium, the size is increasing. Size is increasing. But when you move from zirconium to hafnium, the size is not increasing as expected. Why is it so? Because when you start filling up electrons in the 5D orbitals, before 5D you must have filled 4f. Make sense? Before you start filling 5D orbital, 4f orbital would have been filled. And 4f, we know very well, it has got very poor shielding effect. We know shielding effect of s orbital is greater than p, then d, then finally f. F is of very poor shielding effect. Therefore, nucleus will be very much capable of attracting the electrons present after the f orbital. And what are those electrons? F5d orbitals. So they will be tightly held by the nucleus. The nucleus will not let it increase its size. Rather, it will start shrinking. It will start going down. So there is again a competition. D block elements are very interesting to study, guys. Very interesting to study. So size was expected to increase. I was rather expecting this blue line to be present here. Like that. But is it present? Is it really like that? No. Why? Reason is very clear. Because of the electrons present now. Because of the now electron present in 5f, 4f. The electrons does not shield the nucleus properly. Therefore, nucleus starts attracting 5d electrons, and the metal starts shrinking, or element starts shrinking. The size go little smaller than expected. This phenomena is known as lengthened contraction. Now, if I give you a 4D element and 5D element ka mixture and ask you to separate or identify, will you be able to do that? Very less chances. The chances are very thin. You may not be able to do, because their sizes are similar, and then their chemical physical property will also be alike. You may not be able to separate them by the physical method. You may not be able to decide what reagent should I use to separate them chemically. This becomes a complex chemistry. Hence, we do not have much of these reactions known for the elements, for these particular elements. Okay. Now, ionization enthalpy is also one important question for your board perspective, guys. Why chromium plus 1 is more stable than manganese plus 1? Chromium plus 1 has got 5 electrons present in the D and nothing in 4s. This becomes a stable configuration. Why 5 electrons are stable? As I said, you are supposed to answer in the comment box why chromium likes to have 5 electrons. So I will be also discussing this. Now in manganese, manganese has got 3D 5 4s2 type of electronic configuration. Now when I make it manganese plus 1, one electron will be gone from here, one electron will be removed from here. So how many electrons do you have? 5 in D and 1 in 4s. So this becomes a little weird electronic configuration. You are disturbing this fully filled electronic configuration of 4s and making it half filled. You're making it with just one electron. So removal of electron becomes little tedious. Removal of this electron becomes a little more challenging. So chromium relatively likes to be in +1 state compared to manganese +1. So you should be able to write that properly if it comes to you in your examination. They may also ask you another question, guys. Why manganese 2 plus is more stable than Fe2 plus? Say manganese 2 plus has got no electron in S. Now this becomes highly stable half-filled electronic configuration. But Fe2 plus, which is Fe is having 3d6 4s2 electronic configuration. Am I right, everybody? Neutral Fe. Neutral Fe. Sir, how do we know that? So starting material is this. In the starting, Fe is present over here, 21, 22, 23, 24, 25, 26 electrons. And 26 electrons will be distributed in the valence shell like 3d6 4s2. So manganese 2 plus has got 5 electrons in the valence shell, no electrons in the S, but Fe2 plus still has 1. So to stabilize, it would try to have its 4s2 type of electronic configuration. Here full half-filled electronic configuration, here half-filled, but this single electron is also trying to figure out many ways to stabilize it. So rather it will try to remove itself, rather it will try to leave the system and become Fe3 plus. So Fe2 plus is of less stability than Mn2 plus. Correct, everybody? So if I ask you out of Fe2 plus and Fe3 plus, which electronic configuration, which oxidation state you think is a better one for iron? It is Fe3 plus. Since so far I have not considered any solution ka effect. In gaseous phase, Fe2 plus and Fe3 plus ka comparison. Just Fe, no hydration, nothing, no solvation effect is considered so far. So in between these two, Fe3 plus is supposed to be more stable than Fe2 plus. The reason is very clear. This electron also would like to go away, also would like to leave the system and create half-filled electronic configuration. Okay. Now you might be wondering why these compounds, D block elements, are colorful. When I started working in the laboratory for the first time during my IIT Delhi days, I figured out that there are various compounds which are colorful. People were making the color compounds and going for analysis in the various instrumental rooms. So I also got fascinated in doing some research, doing some work in the field of D block, and therefore I did my PhD in organometallic compounds, organometallic chemistry. So there are two big reasons behind why D block compounds are colorful. One reason is whenever electron jumps from one place to the another. What is the place here in these elements? The orbitals. When they jump from one orbital to the another orbital, they will create some color because they have to come back to their native state, their native or their original electronic configuration, original orbital. And while they return, they have to release the absorbed amount of energy. And that absorbed amount of energy will be released in the two ways, either heat or in the terms of some light. So heating is generally not taken the right path. So what they do, they will start releasing some sort of photons. And that photons will be corresponding to some lambda. Lambda will correspond to a color. Simple, very good. So they will be color to the system. And when can this happen? When can electron jump from here and there? If the electrons are, let's say, these are the two orbitals present. If this is unpaired, this can jump to the higher energy orbital by receiving energy from the surrounding or by any external source. The other one is charge transfer. When metal form bond with another compound, another, let's say, metal ligand bond. So the ligand will start transferring some charge from its orbital to the metal ka empty orbital, and then the color will be very, very, very deep. Relative to this, the color here will be very, very faint or not very dark, I would say. Here the color will be very deep. For example, KMnO4, for example, K2Cr27, they are of very deep color, very dark color. Although there is no unpaired electron, yet there is a possibility of charge transfer which provides a very dark color to a molecule, a compound. This is what we are going to see now. Sir, it means that if there are no unpaired electrons present, there will be no jumping. Hai? There will be no jumping. If there is no jumping, no color. Yes, you understood it right. You found it right, everybody. Let's say vanadium 5 plus. Vanadium 5 plus is going to have 3D 3d3 and 4s2 type of electronic configuration for vanadium neutral. But when you make it 5 plus, these electrons and these electrons, everyone is gone. All these electrons are gone. As a result of this, guys, there will be no electron, no unpaired electron left, and no DD transition possible, and no color to the compound. This is also one of the questions: why copper sulfate? Why copper sulfate has got in the hydrated form, it has got color, but zinc sulfate ZnSO4 has got no color. So copper 2 plus, yes, zinc 2 plus. Zinc 2 plus means 3d 10. Is there any unpaired electron present in 3d? No. But in the case of copper, this has got 3d 9 type of electronic configuration. There is still some scope for some charge transfer or some DD transition. Correct, everybody? This makes the substance colored in nature. Now, there are few trends we need to understand. See, inorganic chemistry has to be studied with electrochemistry. Not that deep electrochemistry, but standard electrode potential. Because we study these elements' behavior in the terms of their oxidation state or reduction state, or their power to undergo reduction, power to undergo oxidation, oxidation power, reduction power. All those comments can be done when you study them in water system, in aqua media. How do we study this system, everybody? So metal starts with its oxidized form, accept a pair of electron and becomes reduced species. So from here to here, the process is reduction. M2 plus receives 2 electron, becomes neutral metal. So if this process has got a positive electrode potential, this reaction is fissile. If this reaction has got negative electrode potential, you need to do some external efforts to make that non-spontaneous reaction to occur. If the E value is positive, if E cell value, everybody knows that, hai? You have studied electrochemistry chapter, I also have taught to you, hai? You can check that in the playlist. E cell, if it is equals to positive, then the reaction is spontaneous. Reaction is possible, spontaneous. But if E cell is equals to negative, is the reaction spontaneous? No. It has to be made. It has to be forced to undergo. So if this has got a positive electrode potential, the reaction is possible. What does it mean now? What's the interpretation? Metal likes to be in its neutral form, not be in the form of 2 plus, not in the charged form, not in the oxidized form. So what M2 plus is going to behave then? It is undergoing reduction. Species which undergo reduction, what are they going to do to others? They will oxidize others. So what will M2 plus be? It will be an oxidizing agent. Are you following, guys? Any species which accept a pair of electron or 1 electron or 2 electron, or whatever number of electron, if it is accepting, in return it will do the reverse process to others. So undergoing reduction here will oxidize others. And anything which oxidizes others will be known as an oxidizing agent. There are various parameters which will define, which will judge, or which will comment on the potential M2 plus to M ka potential. So the first one is enthalpy of atomization. We will be taking a big chunk of metal. That entire chunk of metal is not going to undergo to oxidize or reduced change. So we will be converting it into atom system. We have to atomize that. Okay, at atomic level we study that. Then we have to do ionization. Correct? We have to do first ionization enthalpy, because a metal would first lose its electron to become M plus, then second ionization energy to become M2 plus. So there are 2 ionization processes happening over here. Then finally, as I said, aqua, we study that in water. There will be hydration energy coming into play, which will try to stabilize M2 plus. If M2 plus is happy with water, it will retain its position. It will remain as plus as M2 plus. If it does not like, it will not be there. It will try to come back to metal. So there comes a very beautiful question, very important question. Although the according to electronic configuration, copper plus 1 should have been more stable than copper 2 plus. Do you agree that? Do you agree with me, guys? Let me take that extra slide and ask you, copper plus 1 versus copper 2 plus. Sir, copper plus 1 is supposed to have 3D 10 4s 0 electronic configuration. Copper 2 plus is supposed to have 3D 9 4s 0 configuration. So according to argument so far, fully filled electronic configuration is more stable. Then this is not fully filled. This is 3D 9. This copper plus 1 is more stable than copper 2 plus, in gas phase. In the gas phase. This is a very important question, guys. Very important question. But if you take copper 2 plus and study that in water, copper 2 plus becomes more stable than copper plus 1. Copper 2 plus is more stable. Now the reason is very clear. Reason is very clear. Water is present to actually help it in stabilizing. Water provides it very high hydration energy. And we know from chemical bonding chapter, hydration energy depends upon the charge of the atom, charge of the element. How much charge is that? This is 2 charge, 2 plus charge. How much charge is this? Just plus 1 charge. So water will be attracted towards more positive charge. Yes. So this is the statement. Please read the statement, everybody. The E naught of copper 2 plus to copper is positive because high energy to transform copper solid to copper 2 plus aqueous, please notice aqueous, is not balanced by its first hydration enthalpy. This is a positive value from copper 2 plus to copper is a positive value because the high energy to transform copper solid to copper 2 plus is actually not very good. But once you take copper 2 plus ready-made and then add into, or copper plus 1, I'm saying copper plus 1 to copper 2 plus is a facile process, है ना? Copper plus 1 would like to change to copper 2 plus in water, but taking copper solid, would it go to copper 2 plus? No. Why would it do that? From where will you bring these two high amount of energy? From where will you bring the energy to disturb this fully filled electronic configuration to make 3D9? Did you understand, everybody? Copper plus 1 to copper 2 plus is okay, very good. But when you have copper metal and dip it into water, will it change it to copper 2 plus? Never. And that is the reason we use copper metal in all our electrical appliances, because it hates water. It remains in the metallic form. Now let's come back to our statement. This is a positive value. What does it mean? Copper 2 plus will always try to reduce itself and become metal, right? In water, because water is not a good one, it's not enough, or it's not sufficient to keep that copper 2 plus into copper 2 plus form. Okay, right. So even if I take copper, and try to react it with HCl, you generally you must have studied taking zinc with HCl, taking tin with HCl. They both, or there are various combinations, they are going to produce H2 gas. Therefore we say the set of reagent is reducing agent. It's a reducing agent because they two metal react with HCl to produce H2 gas. Tin reacts with acid to produce H2 gas. But is this possible? Will copper react with HCl to produce hydrogen gas? No. Why will copper? We just came to a conclusion that copper does not want to undergo oxidation. This process, copper to copper 2 plus has got E naught value negative. Copper 2 plus to copper E naught value is positive. So you are never ever going to experience release of hydrogen gas. This is not going to occur. I hope I am clear, guys. Entire chemistry of copper is now discussed. Okay. So I have brought to you a data also. So titanium, this is again M2 plus 2M. So I just told you copper likes to be in its metallic form. Any other element, do you see any other element has got a positive value? No, none other. So copper will become the best choice to make electrical appliances or anything which is exposed to moisture. Right? If you expose them to moisture, will they retain themselves in their metallic form? The chances are very poor once again. So copper is the best choice and it is very good conductor of electricity also. Clear, everybody? Okay. Now there are three elements, specifically manganese, zinc and nickel. They have got relatively higher negative value than you were expecting. Reason behind, M2 plus is more stable, and relatively M2 plus is going to give them either fully filled or half filled electronic configuration. Therefore, they don't want to unnecessarily accept two more electron and disturb their half filled or fully filled electronic configuration. For example, manganese. Manganese is happy being Mn2 plus, relatively happy being Mn2 plus. because it is 3D 5 electronic configuration. I'm not saying that it will not accept electrons. It will accept electrons, but will it accept electron happily? It will do some nakhra. It will show some tantrums. No, I don't want two more electrons. Don't give me electrons. I am okay. But finally it will take. Finally it will take. See this. See, it is going to be an from Mn2 plus to Mn. It's a negative value. Is it possible for it to accept two electrons? In the normal condition, it is not. But you can force it. You can ask it, please take it electron. And then you can supply some electricity. You can do electrolysis. You can ask that this reduction I can perform, but under external forces. For all these elements, titanium, vanadium, chromium, manganese, for all of them, I can do the same. For copper, you need not do anything. You just show it to 2 electrons and it will convert it into copper metal. Copper 2 plus will immediately accept, in a moment time, it will accept 2 electrons and become copper metal. Rest will show some tantrums. Okay? Clear, everybody? Okay. Now this is the very first molecule known as potassium dichromate, having formula K2Cr2O7, beautiful orange color. I remember I performed an experiment during my IIT Delhi days. I took this for our experiment. You start heating it with a heat gun. Heat gun, just like a lighter, you start heating it. It becomes a brown or green color mass in no time. It start becoming green color mass in no time. This becomes one of your experiment also to perform in school exhibition, or you can do it in anywhere. You can do it anywhere, because this is artificial volcano. K2Cr2O7, if I take a huge, if I create a huge collection of K2Cr2O molecules, if I keep them together and just hit it with a lighter ones or a heat gun ones, this will receive the energy and then the rest of the process happens on its own. It becomes spontaneous. You just need to ignite it. Volcanic eruption happens on its own. Likewise, K2Cr2O7 reaction, you just need to ignite it, and then rest this molecule has to do for you. It will start producing lots of Cr2O3, green color mass. It will start evolving from its mouth, from its top. It will start evolving Cr2O3. Chromium 3 plus is green in color. Okay, let us see how do we actually create potassium dichromate in the laboratory or also in the nature. When we fuse, when we mix and heat, fusion means mix and heat, chromite ore is FeCr2O7 with sodium or potassium carbonate, Na2CO3 or K2CO3. Then what is going to happen? This reaction is going to occur, but there is one condition, very important question from your JEE mains as well as advanced as well as for NEET perspective. For board, definitely yes. This requires oxygen. Without oxygen, this reaction is not at all possible. You have to have O2 environment. This is aerobic oxidation in the presence of air. You have to do that. It's an oxidation process. So FeCr2O4 reacts with oxygen in the presence of sodium carbonate. Then you obtain Na2. Do you see what change has happened so far? Earlier you had Fe. Now you have brought in sodium, Na2. This is the major change. This is the change that has happened so far. And to do this, you need oxygen. Okay. Now, this is a yellow color ka solution with Fe2 and CO2 release. CO2 just go away in the air and Fe2O3 settles down. Now I will take this molecule, add a little bit of acid, it gets oxidized to Na2Cr2O7. This becomes this molecule Na2Cr2, sodium dichromate. It is a sodium dichromate solution, sodium dichromate ka compound. It is more soluble than potassium dichromate. So therefore, we do not use sodium dichromate in the laboratory as a primary standard. For any volumetric titration, we prefer potassium dichromate. Again a question, everybody. Again a question, why K2Cr2O7 is used, is prior over or is preferred over Na2Cr2O3? The reason I am telling you, Na2Cr2O7 is hygroscopic. It absorbs water in air. It absorbs, but K2Cr2O7 relatively very less. So if I give you a petri dish or any container which is filled with Na2CO3, today I weigh for you is 10 gram for you, 10 gram, and tomorrow when you come back the weight will be more. So how come the weight has increased? We cannot create mass. Yes, it has absorbed moisture from air. It has absorbed moisture from here. And on the same day, I give you K2Cr2O7 also. Wait, the next day, it will still be the same. It does not absorb moisture. Therefore, K2Cr27 is preferred as a primary standard. Na2Cr2O7 is not. Okay, K2Cr2O7 is preferred. Now, when you add KCl to this, we need potassium source, so there will be cation exchange reaction, metal-metal exchange reaction. So you obtain K2Cr2O7. Beautiful orange color compound. Just looks like motichur ka laddu, है ना? But don't eat it, please. Okay. Now it has a very beautiful reaction, guys. K2Cr2O7, K2Cr2O7, and K2CrO4. These are the two chromium K compounds. This is a compound which has got yellow color. This has got yellow color. This is orange color ka compound. Okay. Chromium here also it's tetrahedral. Both these oxygens are carrying one negative charge each. But this is having one oxygen atom common, shared. Okay. This is also tetrahedral. This is also tetrahedral. This chromium is also tetrahedral. We can interconvert these structures. Take potassium chromate, add acid to it, you will get a dimer. Take potassium dichromate, add base to it, it will break down the molecule to form potassium chromate. This is one of the beautiful reaction you should remember, you should note down. So depending upon the pH of the solution, you can have one of the species in excess, one of the species in higher amount. This is an equilibrium. You can disturb this equilibrium by adding more or less of an acid or a base, depending upon the substance. Okay, both of these compounds have chromium in the same oxidation state, that's 6+. Okay, this reminds me one of the question you have to answer in the chat box, guys. What is the oxidation state of chromium in CrO5? You have to answer this in the chat box, in the comment box. What is the oxidation state of chromium in CrO5? Now let's read some of the properties. So potassium and sodium salt of dichromate, they both are strong oxidizing agent, and we often use this in organic chemistry. So if you take this molecule in acidic medium, it will happily accept 6 electrons to convert into green color ka substance. Chromium 3+ I said will be green in color. Okay, but K2Cr27, since it's an oxidizing agent, it will perform all sort of oxidizing processes. For example, iodide will get converted to I2 molecule. Sulfide will get converted to sulfur colloidal solution. Tin in the 2+ oxidation state will get oxidized to tin 4+. Fe2+ will get oxidized to Fe3+. In all these cases, the oxidizing reagent used is K2Cr2O7. Okay. Now, how do we prepare potassium permanganate? And the formula for potassium permanganate, everybody knows, KMnO4. Again, we use fusion method, and this time we take MnO2, which is also known as pyrolusite. These names come from metallurgy chapter, ores of the metal. MnO2, pyrolusite, with alkali metal hydroxide. What is alkali metal hydroxide? Alkali metal can be lithium, sodium, potassium, all those, rubidium, cesium. And then we need an oxidizing agent like KNO3. What did we use in K2Cr2O7 preparation? Oxygen, air. Here we require KNO3, or we can use atmospheric oxygen as well. That will produce a dark green color compound. What is that compound ka formula? It's K2MnO4. Tell me its oxidation state, everybody. Is it 6+? Yes, it's 6+. Manganese is in 6+ oxidation state. Now when I take MnO4, this is a 4 over here. Let me use a white pen and then mention 4 here. So KMnO4, K2MnO4, or I can just directly write MnO4, 2- charge. Acid is added, it gets oxidized to 7+. What's the oxidation state of manganese here in this compound, guys? 7+. One compound is 7+, the other compound of manganese obtained is in 4+ oxidation state. Let me go through these reactions once again. Take MnO2, fuse it with alkali. So pyrolusite is taken, fuse it with alkali. Take Km and KNO3, potassium nitrate, or you take directly oxygen. It will convert into green color compound. That's K2MnO4, having manganese in 6 plus oxidation state. I will come back to a question, guys. What is the color of MnO4 with 2 minus charge, manganese 6 plus? I will ask you this question in a moment. Don't forget this. Then I have KMnO4. K2MnO4 can be converted to its higher oxidized species like KMnO4 with the help of an acid treatment. Okay. Now, as I said, KMnO4 and K2Cr27, both of them are oxidizing agent. But in laboratory, how we make it? Very simple reaction. We take peroxodisulfate. This compound is known as peroxodisulfate. Again, a question I'm asking you, tell me the oxidation state of sulfur. There are 2 sulfur. Tell me the oxidation state of each sulfur in peroxodisulfate molecule. Peroxodisulfate, and practice its structure also. So I'm giving you a hint that it is going to have this kind of framework. Okay. So Mn2 plus, when it is reactive with peroxodisulfate in presence of little of water, it gets converted to KMnO4 minus. Right? So Mn2 plus is converted to Mn7 plus. Manganese 7 plus. This is how we make KMnO4 in the laboratory. Very simple, very easy reaction. Okay. This is how it looks on a petri dish. If you keep that compound, it is of very high dark color. It forms a dark color, purple color, almost black. It looks almost black. But if you take chunk of very small amount, a flake of KMnO4, add it into water, it dissolves nicely on its own. It dissolves nicely, and the entire flask of water will get converted to a purple color ka solution. Okay, so these crystals are actually isostructural to KClO4. What is the meaning of isostructural? They have same structure. Iso means same. So chlorine has 4 oxygens around it. This is how it will manage. KMnO4 also has got the same kind of structure. Therefore, they are known as isostructural. So this is another question for you. KMnO4 and KClO4, what's the relation between these two? They are isostructural. Not very soluble in water. This is one issue with it, not very soluble. But when it solubilizes, it gives you dark color. But relative to K2Cr27, this is the meaning. This is the comparison done with K2Cr27. Not very soluble. K2Cr2O7 is very soluble. And compare it with Na2Cr27, that though just soluble, highly soluble. Now again, very important reaction, please make a note of this. If you start heating KMnO4, it decomposes to its lower oxidation state compounds. Can you tell me what kind of reaction it is, guys? What kind of reaction is this? Sir, there is 7 plus manganese present here, which dissociates to produce manganese in 6 plus and dissociates to produce manganese in 4 plus. Same species is undergoing reduction 2 times. Reduction 2 times. All right, everybody. Let us go to the next part. What are the properties? As I said, it has got important physical properties. It has got intense color and diamagnetic it is. Bring metal, a magnet near this molecule, it will not be attracted. It's a diamagnetic material. Manganate, which is K2MnO4, as I just asked you that I will be asking this question, it's green color and paramagnetic. Why is it paramagnetic? Again, a very important question. Manganese is having 6 plus charge on it. Due to 6 plus charge, the electronic configuration will be having 3d1 electron, and due to one single electron present, it becomes paramagnetic. On the other hand, KMnO4, manganese having 7 plus charge, and that has 0 electron in D as well as in S. Therefore, it is diamagnetic in nature. Understood, guys? Makes sense? Let us go to the next part. Again, it's a strong oxidizing agent. It can perform various oxidation states. It can undergo change from 7 plus to 6 plus. Yes, E cell is positive. From 7 plus to accepting 3 electrons, changing to 4 plus. Yes, it's also one of the feasible process. 7 plus, it can accept 5 electrons and turn to Mn2 plus. All these reactions are possible. Controlling the amount of H plus will decide what reaction is going to anyways occur. You have to control the acid ka amount. Okay. In acid solution, KMnO4 can oxidize iodide, will convert it into iodine. Fe2 plus, which is green in color, will be oxidized to yellow solution of Fe3 plus. You should know these colors also, guys. They will be helpful for you in your quantitative analysis and in qualitative analysis chapter also. Oxalate, what is oxalate, everybody? Oxalate is derived from oxalic acid. This is the structure of oxalate. This is the structure of oxalic acid, by the way. When you remove both these hydrogens, then it becomes oxalate. Oxalate. This has a negative charge. This also has got a negative charge. That can also be oxidized. What's the oxidation state of carbon here? It's 3 plus. What is this? 3 plus. So it can be oxidized to CO2, where carbon is present in 4 plus oxidation state. All these are acid in the acidic medium oxidation reactions. What can happen when you take hydrogen sulfide, H2S, will also get converted to sulfur. It will start precipitating. Sulfurous acid, H2SO3, or you can take sulfite, है ना? Both of them will be converted. Any one of it. Sulfide will be inorganic compound. Sulfurous acid will be H2SO3. Will get converted to its sulfate. Sulfur in higher oxidation state. Here sulfur is in 6 plus oxidation state, and here sulfur is present in 4 plus oxidation state. Clear? Nitrite can also be oxidized. Nitrite can also be oxidized. What's the oxidation state here? Nitrogen ka 3 plus. What's the oxidation state in nitrate here? 5 plus. So all these reactions are carried by KMnO4. Very useful material, guys, very useful material. In the neutral or faintly alkaline medium, then again, remember, this is very important, very important. Earlier also we had iodide, but in faintly and neutral, what has happened to iodide? It has transformed to, it is changed to IO3 negative. Oxidation state of iodine here is 5 plus. Relative to other, compared to other reaction what we had here, where is it, everybody? We converted into iodine molecule when this reaction was done in acidic medium. But when you take faintly alkaline or neutral, you should remember what happens to iodide. It gets transformed to IO3 negative iodate. Okay. Now, this molecule which is thiosulfate. My question again, please find out the oxidation state of both these sulfurs here and draw its structure. Please practice and find out its oxidation state. Comment me in the chat box. I will come and check that. Okay. So manganese changes its oxidation state from 7 plus to 4 plus consistently, from 7 plus to 4 plus, where in neutral and faintly alkaline medium. So I'm going to give you one beautiful trick, everybody, that is called BAN rule. B-A-N. If you take KMnO4, which is having manganese in 7 plus oxidation state, in basic medium, follow this rule of 153. In basic medium, what is going to happen to Mn7 plus? It will change its oxidation state by factor 1, and the compound formed would be Mn6 plus. In acidic medium, the compound formed will accept, this 7 plus will accept 5 more electrons and gets converted to Mn2 plus. In neutral or faintly alkaline medium, what is it going to do? It will accept 3 electrons to change to Mn4 plus. Just remember this. Now the reactions will be sorted. Here it was neutral or faintly alkaline medium, guys. According to that, my compound of manganese formed should be of Mn4 plus. Is it Mn4 plus? Yes. Is it Mn4 plus? Yes. Is it Mn4 plus? Yes. Let us go to the previous slide and confirm. In the acidic medium, as I said, it should be Mn2 plus, Mn2 plus, Mn2 plus. Previous slide also here, Mn2 plus, acidic Mn2 plus, Mn2 plus. Clear? Okay. Very good. D block over. Finished. D block done. Now let's discuss F block elements. We have got two type of series. One is called lanthanum and lanthanides, or the other one is called actinide series. This is known as 4F series. Total 14 elements are present, and this is called F5F series. Again, 14 elements are present. Now, what are lanthanides basically? Lanthanides are resembling to one another because they have only one stable oxidation state, and that's 3 plus. Lanthanum likes to be in just 3 plus oxidation state. They don't like 4 plus, 5 plus. And there are small change in the size because of which it becomes extremely complicated to separate them, extremely complicated to decide in a mixture of the two metal atoms which element is actually reacting, because they both will showcase similar reactions. Because sizes are the same, their physical chemical property will also be same. Okay, but when it comes to actinide, their chemistry is very complicated, hence we don't study them much. There are not many reactions known to us. So they have got wide variety of oxidation state. This is very important question. Why is it relatively easier to study lanthanum, but very difficult to study actinide? They have wide range of oxidation state. They like to be in +1, 2+, 3+, 5+, times 7+, up to 7+ also. But they like to be in either 3, 4, most of the time 3+ or 4+. Most of the time. They are radioactive, hence they create lots of problem in their study. They're not bench stable. You cannot store them in a bottle. They're not very stable. Okay, so when lanthanum, as I said, lanthanide, when they react, try to be in their 3+ oxidation state, they can react with oxygen to form Ln2. Ln kya hai? What is Ln? Is the common representation for lanthanides. So Ln2, 3 is possible. When you react it with an acid, it will also form Ln3+ and produce hydrogen gas. Correct? With halogens also, it will form LnX3. With base also, with water also, it will react form and it will react to form LnOH whole thrice, and hydrogen gas is liberated. With carbon also, it will form carbide. With nitrogen, nitride. With sulfur, sulfide. All these are possible. Okay, good. Now comes to electronic configuration of lanthanides and actinides. Lanthanide, to be particular, this is very important question, asked multiple times in your exam, many times in your examination. Please notice these red colored boxes. Lanthanum is the first element considered here, but it does not have F orbital. It doesn't have F orbital. So if you write its electronic configuration, it is 5d1. 5d1, it should be 6s2. 5d1, 6s2. Correct? So when you start removing an electron, from where should you remove the electron? From 5 or from 5d or from 6s? You should be removing it from 6s. Suppose I remove 2 electrons, so 5d remains as it is. Now I want to remove another electron. So what will be the electronic configuration? There will be no electron left in D, no electron left in S. There will be no electron in F also. So the question comes to you in examination, what will be the electronic configuration of 4F, of lanthanum? 4F may how many electrons are present? 0, no electron at all. No electron at all. So when we come to cerium, the very first element of this F block element, lanthanide, it has got 1 electron. Please notice there is no element in this periodic table, no element in this lanthanide which has got 4F2 type of electronic configuration. Nobody has that. So you start from 4F1, then directly 4F3, 4F4, 4F5, 4F6, 4F7. And please note, in gadolinium, you have 4F7, then 5D1 comes again. Otherwise, there was no D. Otherwise, there was no D. So this is again an interesting question. When you remove an electron, you should remove it from 6s. Then you remove it from 5d. Then will it let the electron go away? No, because half-filled electronic configuration 4d7 makes it very stable. Very stable. So does this mean if I forcefully make gadolinium 4+, it will try to accept an electron to become gadolinium 3+? Yes, you are perfect. You are perfectly right. So what will be the nature of this guy? It is accepting an electron, so it will oxidize other. It becomes an OA. What is OA? Oxidizing agent. Oxidizing agent. Likewise, lutetium, let me pull the slide a little bit up. Now. Yes, now it is visible to you. Lutetium would like to have 4F14 by losing electrons. So 4F14 can be possible in 3+ oxidation state. Now you can witness 3+ oxidation state is the most stable for lanthanides. Correct, everybody? Okay. Okay. Very good. Very good, guys. So this is my atomic and ionic size of lanthanide ka comparison. Please notice this from lanthanide up to the lutetium, you are constantly seeing that the size is decreasing. The size is decreasing, and this regular decrease in the size from La3+ to Lu3+ is called lanthanide contraction. The size is constantly decreasing. You can ignore this, you can ignore this for time being. Nobody will trouble you with these corner cases. and greater effect of the increased nuclear charge than the screening effect is one of the reason why they have similar sizes. In this case, the size is decreasing, but otherwise they do not have very different sizes in their elemental form. Okay. Oxidation state of these element, as I said, this will be 3 plus. So in some cases 2 plus and 4 plus is also possible. Who all are those metals? Which are those elements, guys? If you by chance obtain F0 element, F0 state, or F7 or F14, they would like to be the more stable. They would like to be in that particular state. So let's see some examples, everybody. You have cerium. Cerium has got electronic configuration 4f1, 4f1, 5d1 and 6s2. 6s2. Now it says, let me remove all of my electrons so that I am empty. I have no unpaired, no here and there electron. So cerium says I am fine. Cerium says I am fine. Similarly, you have another element which can also showcase 4 plus oxidation state. See, here we had a full table. Here we had a full table. So I said cerium is the guy. Cerium is that guy which can have 4 plus oxidation state, and then we have terbium which can have 4 plus oxidation state. Reason is very clear. Here you will manage to have 4d7. Check please. Here you can manage to have 4d7 after losing one more electron. 4d7. 4f7. 4f7 after losing one more electron. What about this one? It says I want to be in 4f0. Very good. Very good. Then finally, these two, just these two would like to be in their 4 plus oxidation state. Very important. Please make a note of this, guys. Please make a note of this. Okay. Ce and Tb. Both these. Therefore, cerium 3 plus versus cerium 4 plus. If I compare these two, it likes to go to here, or does it like to go from 3 plus to 4 plus? This is the process. So it wants to undergo an oxidation. If it is undergoing an oxidation, so cerium 3 plus will be a reducing agent because it wants to undergo oxidation. But cerium 4 plus will be an oxidizing agent. Are you understanding, guys? Batao bhaiya. Is that clear? Are you following? Oxidizing agent, and this is called reducing agent. Oxidizing, this reduction process, this is called a reduction process. This is oxidation process. Clear? Okay. Very good. Now comes to this molecule which has got electronic configuration 4f7, 6s2. It says, let me remove both my electrons, and I am happy with half-filled electronic configuration 4f7. Okay, 4f7. And here you can let these two electrons also go. So they would like to be, let me mark that in the periodic table here. So they would like to be europium 2 plus, and then we had ytterbium. They both like to be in their 2 plus oxidation state. 2 plus. So please see that this is 4f14. Very good. And here it is 4f7. Very simple, everybody. Just remember these 4 cases. You will be done. 5 cases rather. You should remember cerium likes to be in 4 plus. Very good. Terbium likes to be in 4 plus. Very good. Ytterbium likes to be in 2 plus. Very good. And then we have which one? Yeah, europium also wants to be in 2 plus. Reason are clear. 4 plus because they will have half filled or fully filled. 2 plus also because they will have half filled or fully filled after losing these much electrons. Okay, that was from your F block. That was from your F block. This is what I have just discussed. If cerium can also do that same, if cerium wants to go to 4 plus oxidation state, this will also try to go to 4 plus or not, that we have to discover. So from here to here, Tb here, from here to here, is that possible? Or from here to here, is it possible? We just have learned that. Tb, Tb, let's say terbium. We just learned that terbium wants to be in its 4 plus oxidation state. Like cerium 3 plus to 4 plus is a reducing agent. So what will terbium 3 plus will be? From terbium, from here to here, it would like to undergo an oxidation. This becomes a strong reducing agent. From here to here, if you want to go 4 plus to 3 plus, no, then it becomes strong oxidant. Everybody, because it likes to be in 4 plus oxidation state. So if you are offering it an electron, it will become Tb3 plus. From here, when you go to samarium can lose its electron and become 3 plus. Remember, overall, everybody, Overall, 3 plus is the best stable oxidation state for them. If anyone is present in 4 plus oxidation state, it will become strong oxidizing agent. If anybody is present in 2 plus oxidation state, it again wants to become 3 plus oxidation state compound. So anybody who wants to accept an electron becomes a strong oxidant. If anybody wants to lose an electron, will become strong reductant. Clear, everybody? Okay. Now comes to actinoid. Actinoid also have got a list of elements here. You need not remember all of these. Just remember their electronic configuration, general electronic configuration. Make sure you know that there is a possibility to have 0 or 1 electron in 6D. 0 or 1 electron, and 7s is always fully filled. Then you can have at least 1 electron in F and range up to 14. Range up to 14. Okay. We know when you move from left to right, just like lanthanide contraction, we have got actinide contractions also, and here the contraction is even severe. Why is it even severe? Because the F orbital earlier was just 4F in case of 4F series. In this case, actinide series, we have 5F orbital also. So there will be contribution from two poor shielding orbitals, 4F and 5F. Together they are going to poorly shielded nucleus, and size will extremely be compact. The size is going to decrease a lot. So poor shielding effect of 5F, and before that there is 4F also present. Okay. As I said, oxidation state, there is a variety for these actinide. They just don't want to stick to 3 plus. They want to have a variety of it. So ranging from 3, 4, 5, 6. There is this guy called Neptunium, which has got a variety. Then Plutonium also wants to be the best. They want to compete among themselves. I want to have more types of oxidation state, many types of oxidation state. That makes it a challenge. Actinide, study of actinide is a very difficult task. They are silvery in their appearance, as I said, highly reactive, specifically when they are finally divided, finally in the powdered form. They will be exposed to air to a greater extent. They will start reacting very well. So they are paramagnetic material, and they will tarnish in air due to oxide coating. You leave that piece of metal in air, it will start developing some coating of tarnished metal oxide will be started forming on the top, on the surface. The general symbol for actinide is An, just like for lanthanide is Ln. An is the symbol. Ln also reacts with HCl to form hydrogen gas. Yes. It also reacts with nitric acid. No, it does not react with nitric acid. You should remember. With hot water, it can react, forms two types of compounds. One is called hydride. The other one is oxide. Will it react with the base? No, it does not react with the base. You should remember, it does not react. When you heat this metal with hydrogen gas, you may obtain hydride AnH3. Halogen also, they will start forming. Generally, they form AnX4. In lanthanide, it was LnX3. They react with oxygen to form a high type of compound, the An3O8 type compound. But in the case of lanthanide, it was Ln3O2. Okay, Ln2O3 type compound. Okay. That is it, guys, in your lanthanide and actinide discussion, and D block, entire D block is also discussed. I believe that this was a good revision for you. And inorganic specifically, if you want to study, you should refer NCERT. There is nothing else you require. Plus, watch this session, guys. So your notes are also ready. I have compactly designed these slides for you so that you need not write extra thing. You need not write it again. Just download these slides and you are done. I will see you in the next summary series, summary lecture, everybody. Till then, stay safe, study hard.